Okay, so in class, we built upon that electron configuration podcast video that you watched and filled in pages 7 and 8 from. If you haven't watched that video, you need to go watch that one first, because all of this is going to be variations on those electron configurations, and we're generally going to start with one of those configurations and use that to write it or change it into another form. The other thing you need to have is a periodic table handy. If you don't have a paper version, you need to pull up a digital version someplace where you can at least see it and look at it and find the elements that we're doing and follow through the periodic table, because this is our map for doing electron configuration. So it's really, really important that you have one nearby. Otherwise, everything you're writing down is just nonsense. So please get one out and have one nearby. And the other thing to keep in mind is if you're getting stuck and lost on these problems and it's just super duper confusing, I would prefer that you stop watching this video and come ask me questions. Don't just write it all down and or Google the answers just to fill it in. I want to help you understand what it is, because I know that sometimes these processes can seem like I'm speaking another language, and I want to help you get to speaking this language, and you probably just need a few simple tools in order to get you there. And on that note, if you have these labels in your periodic table in the same space as those element squares, I see people do a whole lot better at this electron configuration stuff. So get your map fully labeled. Put these labels in there so that you can follow with me and go row by row and understand, 2s2, 2p6, 3s2, 3p6, and follow along with me. So, the first variation of our electron configuration, and please write down this description, kind of instruction piece at the top of page 9 where you see orbital notation written. In orbital notation, we are going to represent our electrons as arrows and our orbitals as lines. So we're actually going to be drawing out all of the electrons in a specific atom, but instead of just as random dots around a nucleus, we're actually going to draw them in their orbitals around in a kind of straight line. Now, what you see down below is not anything that you need to fill in. This is, in fact, the longest possible set of lines that we could put together for the biggest atom, OG, on the periodic table. So it's really just here as an example, but if you look at that, you might start to see there are some patterns in the number of lines that we've drawn for our s, p, d, and f orbitals. And that's one of the things that's going to be really important that we write down. If you look at this, all of the s orbitals, whether it's a 1s, 2s, 3s, 4s, all the way down to our 6 and 7s, all of these orbitals have one line. Just one line of all of our s types. And every time you draw out the lines for any s orbitals, you're going to draw one line. If you look at all of the p orbitals here on the page, you probably see they're all in sets of 3 lines. Whether it's a 2p, a 3p, or the 7p, it's 3 lines every time we've got p orbitals. D orbitals are sets of 5 lines, and f orbitals are sets of 7 lines. And especially if you've recently watched that electron configuration podcast, this 1, 3, 5, and 7 probably is a little bit familiar. This is the number of orientations, the number of different orbitals of each shape on each energy level. We said that there was only one s orbital, and that meant it could fit a maximum of 2 electrons. But there were 3 different orientations of p orbitals on each energy level. That px, py, pz that I printed out for you on the previous page. So these match up with those. The only thing that we're doing here is drawing those fancy shapes as simple lines. It makes it a lot easier to find our electrons and to draw those in. So each orbital, each orientation on a specific energy level is its own separate line. Now, we're going to start in these first few examples by filling in arrows to pre-drawn lines so that you can just practice with some of the rules for how we draw arrows. But in general, In a test question or a quiz question, you're going to have to draw your lines, label them with the correct orbital name, and then draw the arrows into them. So lines, labels, and arrows will all be up to you. But we're going to start simple because there are some important rules for how we fill in these arrows. And they're actually sitting back at the bottom of page 8. You probably don't need to flip back and make any notes on them. They're pretty straightforward, and once you do a couple orbital notations, they should be pretty easy to remember. And the first rule is that anytime we have multiple electrons going into the same set of lines, we're going to place them each on their own line first instead of doubling them up first. And the reasoning for that is that electrons are all negative. They repel each other, so they don't want to be shoved close together, paired up in the same orbital if there are empty orbitals. It's probably kind of like you and your siblings. You wouldn't want to share a room with your siblings if your family has 3 spare bedrooms still available. You'd always be arguing with your parents about why can't I have my own room? Well, the electrons repel each other way more than siblings repel each other. So when we have lines, if this was something like blah, 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 3d4, the d orbitals get 5 lines, 5 separate orbitals, and we have 4 arrows to put on them. Well, that means each arrow gets its own line. And yes, we would still leave that empty line there. That actually tells us something about the atom and how it's going to act and react around other elements in atoms. Now, the other rule is when we do have to pair up our electrons on the same line, they have to go opposite directions. And this really does come back to some quantum mechanics about electrons and their spins. But if we have to double up, just make sure they're facing opposite directions. 1 arrow up, 1 arrow down. So let's go add some arrows to some lines. And like I said earlier, we're going to use the electron configuration for each of these elements as a guide in order to fill in these arrows onto our lines. So our electron configuration for oxygen, I'm just going to kind of write it up here, is 1s2, 2s2, 2p4. And if you don't understand how or where that came from, please come in and ask for help. But when we're looking at this term, notice this first 1s2, we're going to be filling in 2 electrons, that's what that exponent tells us, 2 electrons, meaning 2 arrows, onto our 1s line. And it shouldn't come as any surprise that that s orbital gets 1 line there. So we're going to put 2 electrons on 1 line. That means they have to be going opposite directions. Now, something that I want to point out to you here is that my arrows, when I draw them on these lines, don't look like the arrows that I normally draw. Because if I try and start making my arrows go opposite directions on these same lines, sometimes they start running together and looking like some weird triangle or trapezoid shape there. So to save a little space and to look neater, I kind of do a half arrow in each direction. They've still got that half of the head giving them a direction. It can't just be lines. It has to have a direction. It has to have that spin component. But I leave off that inner half so that they don't run together as much. And it doesn't matter whether you do down up or up down. I've just been doing this over and over again for longer than y'all have been alive, so I usually do up down, but it's up to you. Now our 2s line is also going to be getting 2 electrons on it, so 1 up and 1 down. And then our 2p lines are going to get 4 electrons, 4 arrows onto them. And this is when it's important that we put 1 on each before we double up, or really that it ends up with 1 pair of electrons and 2 unpaired electrons in their own separate orbitals. I'm not going to be looking over your shoulder on the test. If you know 4 arrows, 3 lines, 2 of them are going to have to share a line, and you draw them out like this, that's absolutely fine. I'm not going to look at what order you drew your lines in. It is important, though, that those unpaired electrons be going the same direction. So if you do draw them out one by one, start all up or all down, and then when you go back and double up, start going the other way. Not just up, down, up, down, up, 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 down, down, down. Like, keep it consistent. Go all the same direction before we go back and start filling the opposite direction. Once again, more quantum mechanic rules, but it's simple enough to follow. Now, our chromium configuration is a little bit longer, so I'm going to point out to you real quick where it's at on the periodic table so you can follow along with your own. We are coming down here into the first row of our D block to our chromium example. So we're going to keep going until we get to 3D, 1, 2, 3, 4. Remember to go row by row. We're going to start at 1s2. Then go to the second row, 2s2. Don't forget about the p's over there, 2p6. We're going all the way to the end of the second row. And then the third row is going to look a lot the same. Start the third row with 3s2. Finish it out with 3p6. And then the fourth row, we're almost there. We always start with those s's, so 4s2 gets us through the s block, and then ending at 3d4. Now, if we take that term by term, our 1s2 means our 1s line gets 2 electrons. 2s2, 2 electrons, 2 arrows being drawn. 2p6, 6 arrows, so 1 on each before we go and double up. Or, 6 arrows on 3 lines, they're all going to be doubled up. 3s2, 2 arrows here on our 3s line. 3p6 is going to look a whole lot like our 2p6, so I'll go ahead and fill them in. Doubled, 4s2, 2 more arrows for that 4s line, and then 3d4. We've got 4 arrows to put out and 5 lines to put them on, so they're each going to have their own line. Took a little bit to get there, but once you got the configuration, it's really just about calmly following through those rules. So let's try some where we have to draw the lines ourselves. I'm going to do sulfur completely with you, and then I'm just going to give you the configuration for calcium, just like I did in class, and let you use it as a guide to draw it out yourself. And then I'm not actually going to finish up chlorine at all. I expect you to do that, and if you're uncertain of your answer, check it with me. So, sulfur's full electron configuration is 1s2, 2s2, 2p6, 3s2, 3p4. So if we look at this one term at a time, 1s2, because that's an s orbital, we draw one line, and we have to label that line. And then because it's not just 1s, it's 1s2, we have to put 2 arrows on that line to represent those 2 electrons. Then we move on to the next term. 2s2 is also an s orbital, so it's also getting one line because it's an s. 2s2 means 2 arrows on that line. Next we've got 2p6. Now we're switching to p orbitals, which means we need to draw out 3 lines. They're all part of those 2p orbitals. I like to draw these little brackets to help make sure that you can tell all of those are part of the 2p's, because sometimes these can get pretty tight, and if I just write 2p here, it's not as clear about where those lines belong. But if you have enough space to separate them out, sometimes even this works well enough. But I always make sure it's explicit. And then we're drawing 6 arrows on those lines, so they're all going to be full and doubled up. Moving on to the 3s2 term, we're back to s orbitals. S's get one line. We label it, 2 arrows, and then finally 3p4. 3p is going to mean 3 lines because it's p, not because it's a 3 in front of it. Make sure that belongs to all of them. And then we are only going to be putting 4 arrows on these lines, so 1 on each before we double up. Notice how this looks almost exactly like oxygen's electron configuration, at least that end term. Its 2p orbital just looked exactly like S's 3p orbital. And because of that, they're going to act and react very similarly because their electrons are positioned similarly. Even though we had 4 electrons when we went into that 3d4, that one looked different. So it's going to act and react differently than oxygen and sulfur do. So just something we're going to be doing with this information as we move forward. We're going to be using what we know about the orientation and configuration of these electrons to help us learn about atoms. Now, like I promised, calcium's electron configuration is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. So that is its configuration, and you can use that as a guide to draw out your lines, label them, and add your arrows. Chlorine, on the other hand, is up to you. It's actually a little bit shorter than that calcium example. So if you can write your configuration, you can write your orbital notation. But if you can't, please come in and ask me for help, because I want to get you feeling more comfortable with those configurations. Now I am going to move on to the next type of configuration, the next variation on these electron configurations. So if you want some practice with this, you can go and jump to pages 11 and 12 and do a few of these orbital notation. It's the B part of those pages. So you can start by writing out the complete electron configuration in part A, then use that as a guide as you do that orbital notation in part B. And if you're asking yourself, well, Mrs. Gunter, how am I supposed to finish this out? What is a noble gas configuration? Well, I'm about to show you. The noble gas configuration is sometimes called the shorthand electron configuration. It's a shortcut because by now, especially if you've done some practice on pages 11 and 12, you're probably a little bit tired of writing 1s2, 2s2, because almost every single atom, you're having to go through those same two terms and then farther. It gets pretty repetitive, but if we need to know where every single electron is in an atom, then that's the only way to describe it. We got to start at the center and build our way out. But sometimes, and a lot of times, in fact, it's the outermost electrons we care about the most, not those inner ones. So we can skip past those to the ones that are really important. But we can't just leave them off completely. We have to kind of say, oh, we've got some stuff in the middle and then the important stuff out here. We do that using this noble gas configuration. We're basically going to put a noble gas, which is the last column of elements in the periodic table. These guys, we're going to use these as our landmarks, and we're going to put them in those square brackets and then start the rest of our configuration from that point. And the reason that we use these is because they're at the end of the row, so we can still keep in the entire final row of wherever our element is at in our configuration, which always includes the most important electrons. So these elements here, these 6 elements, are the only ones that we can put in those square brackets. It has to be a noble gas. Like I said, this is kind of like taking a shortcut at giving directions. And can you imagine what it would be like if I gave you directions with a landmark you didn't know the way to? Like, I could tell you exactly how to get to my house. You just need to go 2 houses south of Holford Park. But you don't know where Holford Park is. It's a random little park, and no matter how good my directions are, if my starting point, my landmark, is not one that you know, sorry, you're not going to be able to find your way. So we have to use these noble gases because all the elements know how to get to these noble gases. These are the big landmarks on the periodic table. So those are the ones that we use. And which one we use for a specific element also kind of matters. The first example we're going to be writing out is the noble gas configuration for magnesium. And that magnesium is here at the very beginning of the 3rd row. In order to get there, we had to go across the 1st row past that helium noble gas, all the way across the 2nd row past that neon noble gas, and then just a little bit farther. We always want to use the last noble gas that we pass through on the way to our element. So in this case, that would be neon. So we're going to start magnesium's configuration by putting neon symbol in those square brackets, and that neon is sitting there at the end of the 2nd row. Where do we need to go to get to magnesium's house if we're sitting at the end of the 2nd row? Well, to the beginning of the third row where we have that 3s orbital, and then we go 2 squares in, and we're at magnesium's house. So this is our noble gas configuration for magnesium. Gold is a little bit longer. In fact, gold was the last element we did as part of our podcast, and I'm sure by the time you were done writing it, it felt like your hand was falling off. If you find gold in the periodic table, it's element number 79. It's pretty far down there, and we passed by a lot of noble gases on the way there. But the quick, easy way of figuring out which one to use as our starting point, which one was the last one we passed by, is go a row up and then all the way to the end. And that's the noble gas that you should be starting with, because that's the last one you pass through, the one on the row right above your element. And that works even for things like iron here. If you go a row up, there's no elements there, but there is still a noble gas at the end of that row. So it's just the last noble gas that we pass through. So for gold, it's going to be xenon. So we're going to put xenon in square brackets, and xenon is sitting there right at the end of the 5th row. So where do we go after the 5th row? Why? Down to the 6th row. And remember, after the S's in that 6th row, we have to jump down through those F's because they're actually there at that bold line where we normally jump across into the D block. That bold line reminds us to jump down and go through that first row of the F block before we can come back and finish up those 9 squares in to that 5D block. So my hand's not falling off at all. 4 terms is real simple to write down and real easy, and it has all of our most important electrons, so we're not losing any real meaning here. So at this point in class, we moved on to these next 4 examples, and I offered to do 2, any 2 that they wanted to in class, but I've already pointed out the most common question I got about iron was which noble gas to start at, and if you jump back in the video, I already pointed that out to you. Sulfur's pretty short as well, so here in this video, I'm going to do borium and xenon. And I'm actually going to start with xenon, because the question that I get most about xenon is, well, Mrs. Gunter, it's a noble gas. And it most certainly is. It's sitting right over here. And they ask, Mrs. Gunter, can't we just put xenon in square brackets then? And my response is, well, if you were asking me how to get to xenon's house, and my response was, you go to xenon's house. Is that very useful or helpful? No, it doesn't tell us anything that we didn't already know. So just like any other atom on the periodic table, if we want to write the noble gas configuration for xenon, we need to go and start our noble gas configuration with the noble gas that's on the row above the element we want to get to. So for xenon here, we need to start at krypton. And if we start at krypton, sitting there at the end of the 4th row, we just have to come across the 5th row. So 5s2, 4d10, 5p6. Pretty easy. The other one that I offered to do was borium, and first, let's find borium, because it's way down there. It's element number 107, and if we look at the row above, all the way at the end, we're going to be starting our noble gas configuration with radon. And then let me remind you, as we come across our 7s, as we get here to this bold line, that means we're going to come down and go through our 5F and then finish up with our 6D. So, radon, and then 7s2, 5f14, because we want to go all of the way through those Fs, and then 6d, 5. So go ahead and try the same kind of thing for sulfur and iron. Check your answers with me in class if you need, and then you can do all of those part C's on pages 11 and 12. And if you want to practice a little bit there before finishing out this video, I would understand, but we're going to go ahead and move on to finishing up talking about our valence electron notation and our Lewis dot diagrams. So, first off, you've probably heard of valence electrons before, even if it was just one time in middle school. Valence electrons are the most important electrons in an atom. They're the ones in the outermost energy level, and the highest one up the farthest from the nucleus. And if you remember, in all of these configurations we've been writing, way back at the beginning of this page 7, I suppose, I told you that that big number in our terms of the configuration represents the energy level. So this 4s2 is the fourth energy level spherical shaped orbital that has 2 electrons in it. And so that's going to be important as we start to try and find our highest energy level electrons, because they're going to be the ones that have that highest, biggest number in front of their letter. So valence electron configuration is only going to include the terms that are on that highest energy level, and it'll only be 1 or 2 terms. So this is sometimes even shorter than that noble gas configuration, but they're not necessarily unique to a given element, but it helps us focus even more on those most important electrons. Now, what I think is helpful to get down in addition to these definitions is a single example where you can see all of these other types of configurations. Now, if you don't have space to write the full configuration, the noble gas, and the valence here, then I would recommend you just write the noble gas and the valence configuration to show how, for selenium specifically, these 2 configurations compare to each other. But if you have space to put all 3 here, I think it can be helpful to help you understand how we can move from one to the other and how they relate to each other. So as you see here, if I'm trying to find selenium's full electron configuration, we start all the way back at 1s2, 2s2. Those are not the highest energy level electrons because they have really small numbers in front of their letter. If you look at all of the energy levels and all of the terms of this configuration, then the highest energy level electrons are the ones in the 4s2 and 4p4 terms, because those have the biggest number in front of the letter. And those 2 terms are all that we keep in our valence configuration. Just those 2, just smacked right against each other, done. The good news is, even though our full configuration is really long and it will always be able to help you find those highest energy level electrons, when we shorten down our noble gas configuration, because we always have that full final row, it will always contain all of the valence electrons too, as well as some that aren't valence electrons and some parts that we don't need to keep in our valence configuration. So once again, we can see those highest energy level electrons by finding the number that's the biggest in front of the letter. And so even if you want to start with the noble gas configuration to help you write your valence configuration, you'll always get all of the terms that you need for it. So I'm going to help you write some valence configurations for these elements that are down below. And I'm going to start with either the full configuration or the noble gas, kind of just depending on how long it is. Aluminum, that's not too long. That's just 1s2, 2s2, 2p6, 3s2, 3p1. And if you pay attention, each of those big numbers is our energy level, and the biggest of our big numbers, the biggest, highest energy level we've got, is the 3rd energy level for aluminum. And if you look at those exponents, that tells us how many electrons we have. But we don't care about that right now. We'll get to that in the next step. All we need to bring down is both of those terms, 3s2, 3p1. That's the valence configuration for aluminum. Now, tin is a little bit longer, so I'm going to write out its noble gas configuration here. And if we look at our big coefficients, the numbers in front of the letters, the biggest is 5. So our 5th energy electrons are the ones that are our valence electrons. And we're just going to bring those 2 terms down. And that's our valence configuration for tin. Beryllium, it almost seems silly to write out a noble gas configuration for, because it's just 1s2, 2s2. But even here, you can see our highest energy electrons are in the second energy level, so our valence configuration is just 2s2. It can just be one term. It doesn't have to be two, but the longest it will ever be is 2 terms. If we finish this out with iron, I'm going to write out its full configuration. And if you look at that, our highest energy level electrons are in the 4th energy level here. So it is also going to have just one term as its valence configuration, just 4s2. And that might help you see and understand a little better why those D block elements, why we only have 2 terms maximum, because the D block always drop down. Here we had the 5s and the 5p, but the D dropped down a level. And nothing below that last row is ever going to be valence, because as soon as we start that next row, we're going to have a bigger number there. So our valence configuration should only have s and p electrons in it ever. Now, let's move on to something that uses our valence electron knowledge, and that's our Lewis dot structures. We're going to be drawing these structures to represent our electrons, and they're a little simpler than those orbital notations, because we're going to start with an element symbol in the middle, and then we're going to draw dots around the edges around that symbol. And I kind of imagine a little invisible box around my symbol, and we're going to put dots on the side of that box, not on the corners, but on the sides. And at most, we can put 2 electrons on each side of our element's symbol. But when we're placing them, just like when we're placing our arrows on our lines, we're going to put 1 dot on each side of that element symbol before we start doubling up. Our electrons are still going to repel each other. They still want their own space if they can have it. But eventually, at most, we can have 8 dots around our atom, so 2 on each of these sides of our little invisible box. Now, to help you in finding how many dots, how many valence electrons each of these atoms has, I'm going to write out its electron configuration here so that we can kind of analyze it together and count how many valence electrons it has. So, first, lithium, 1s2, 2s1. So, our highest energy level is the second energy level, and hopefully you agree there's 1 electron on that second energy level. So that means that lithium has 1 valence electron, and we're going to put 1 dot on one of those sides around its symbol. Doesn't matter which side it is, as long as it's on one of those sides. Now, as we move to beryllium, beryllium is right next to lithium. And I purposely chose these elements that were right next to each other because now my configuration for beryllium is 1s2, 2s2. So we're still looking at that second energy level as our highest energy level. But now, hopefully it's quite obvious, there's 2 electrons on that second energy level. So our beryllium's Lewis dot diagram is going to have 2 dots around beryllium's symbol. And what's important isn't what sides they're on, but as long as they're on separate sides. They cannot be on the same side together. These electrons want their own space if they can. So here I went to the side. You could do top and bottom or left and right, as long as you got 2 dots on 2 separate sides. As we keep going across that row over to boron, that's 1s2, 2s2, and then it builds up to 2p1. Here, the second energy level is still our highest energy level, but we've got 2 terms, 2 different types of orbitals that are both on that second energy level. So we have to add together the electrons on the second energy level s orbitals along with the second energy level p orbitals. And 2 plus 1 gets us 3. So boron has 3 valence electrons, which means it gets 3 dots. As we keep moving forward, hopefully you're starting to see a pattern emerge. As I move to carbon, then it doesn't stop at 2p1. It goes 1s2, 2s2, 2p2. We still got second energy level as our highest energy level, but this time 2s electrons plus 2p electrons gives us a total of 4 valence electrons for carbon. So it gets 4 dots, which means 1 dot on each side of that symbol. And I could keep writing these configurations, and I will, but you can probably already guess that nitrogen is going to get 5 dots because it ends at 2p3. And it does. So 5 dots means there's going to be 2 paired up on one side and then 1 on each of the other 3 sides. Oxygen is going to get 6 dots because its configuration ends at 2p4. So we have 4p and 2s electrons on our oxygen's second energy level. And we just need to make sure that 2 of those end up paired into 2 pairs, and then 2 separate little lonely electrons that are unpaired. Then fluorine is going to have 7 dots around it, meaning only one side is unpaired because its electron configuration ends at 2p5. So 2 plus 5 gets us 7 for 7 dots. And then finally neon gets 8 dots. It ends at 2p6. So those 6p electrons along with those 2s electrons gives neon 8 valence electrons. So we've filled in all of our dots around these specific elements. But what I want to do to help you understand a pattern real quick that you may or may not be completely aware of is write out one other element's noble gas I could do noble gas configuration. That'll work. So argon's noble gas configuration is neon, and then 3s2, 3p6. Our highest energy level is the third energy level, and notice how it, just like neon right above it, has 8 valence electrons, 8 total electrons on its highest energy level. The only difference is that argon's highest energy level is the third energy level instead of the second. And so by this fact, what we should write down is one last quick note on this section of our paper is that elements that are in the same column of the periodic table have the same number of valence electrons. So as I'm asking you to write the Lewis dot diagrams for these 3 elements down here, you need to go and start by finding those elements in the periodic table. And so once you've found those elements, because selenium is in the same column as oxygen, we already drew oxygen's Lewis dot diagram, and I drew one for every element in that second row on purpose to help you use those as a guide. Selenium's Lewis dot diagram is going to look identical to oxygen's, except it's going to have Se in the middle instead of O. For that matter, krypton is going to look a lot like neon, and calcium is going to look a lot like that beryllium example that we did. So you just need to find where the element is in the periodic table, and that can tell you the number of valence electrons. Now, we're going to talk more about this in general, but in our ION podcast, I'm going to point out to you that all of the columns have this little number at the top of it. And that number can actually help you remember the number of valence electrons for that column. The first column says 1, 1a, 2, 2a. Then when we jump across to boron's column, you have to make sure no atom has 13 valence electrons. So you need to start looking at the A labels, at least by the time you get to this side. If you want to look at both at the A labels all the way across, you can. So carbon's column has 4 valence electrons, nitrogen's has 5, oxygen's has 6. So those A labels at the top of the periodic table will help us in general as we move forward remember our number of valence electrons for each element in that column. So remember to finish up these 3 examples here at the bottom of the page. You know, I tend to check those for correctness and completeness when you turn in your packets. And then if you haven't already, make a start on your pages 11 and 12. You don't have to do every single example right now. but do a few so that you've practiced the same element with the full configuration, the orbital notation, and the noble gas. And then maybe skip to pages 13 and 14, where you're actually kind of practicing analyzing some configurations or finding elements using the configuration, telling me whether they're correct or not, remembering what these things mean. Questions 12, 13, and 14 are a little bit higher level. Remember, we can draw orbital notation to see when our electrons are paired or unpaired. So those could help you with these answers here, even though it doesn't say. Draw the orbital notation. That would help you answer these questions. But if you're getting stuck or you don't know how to do them, come in and I can help you with those problems specifically in class or in tutorials. And so I think page 14 is a little bit simpler, just has you focus on a few types of configuration for different elements. So I hope that helps with your electron configuration variations. And like I keep saying, if you have questions and you're not understanding one of them, come in and ask for help.